All right, let's start. You already saw gamma ray spectrometers in the lab. Let's go through in this presentation all those things once more so that you can have a good impression what happens when we do measurements and spectrum analysis. So these are the contents. What is a gamma ray spectrometer? How the spectrum is generated? How activity or activity concentration is calculated? I have a short some slides only for the peak efficiency. I will talk these things later. What are the requirements for the sample? What does the spectrum analyzer do? And a short summary. All right. So this is a gamma ray spectrometer. The detector itself is located in this part of the detector. This is lead shield. This is the cooler or devar. There is here at least liquid nitrogen, temperature around -200 or something like that. So what happens in the measurement? So the sample is just put on the detector. It's a very simple process, basically. This is a zoom picture. This is the sensitive part of the detector of the radiation. In this case, the diameter might be 7-8 centimeters, thickness around 3-4 centimeters. Not very big. This is so-called planar detector, this one. And this is the detector window. Radiation, gamma radiation goes through that window. If we want to detect very low energy gammas, we should have a very thin window. In older detectors, this window is quite often composed, for example, aluminium, which is also quite good material, but then we cannot see very low energy photons. This window could be also, for example, beryllium material. All right. So, once more, this is so-called active part of the detector, this one. This is an X-ray picture of one of our detectors. So what happens in the detector? This is the detector itself. So gamma goes, for example, this way. Electrons and holes are produced, and signal processing system collects the signal, analyzes it, and put the data into a multi-channel analyzer, from which we get a spectrum. Okay. This is one of our detectors. Lead shield is like this. We have a devar, this part of the detector. We don't have here in my organization anymore those analog measurement systems. We have only digital ones. So you cannot see practically here the MCA. Let's look at what happens here. So this is one of our samples. I will explain later. So putting the sample is a very, very simple thing. There is not a complex process. After measurement, 1 day, for example, then sample is taken out. All right. So how the spectrum is generated. I explained the basis in the previous lecture. Let's look at closer the things. So we have peaks in the spectrum. So how we do the radionuclide identification? It is because of the energy. For example, in this case, the energy is 364 kiloelectron volts, which means, according to the radionuclide library data, this is iodine. So, how to calculate the activity? It is based on the peak area. How many counts are in this peak? Basically, it's a quite easy process, but not always. This is only part of the spectrum, not the whole one. All right. So, these peaks appear so that, let's assume that this is a detector, and photon comes to the detector. What happens? They may have multiple interactions or only one interaction. The point is that all the energy is detected by the detector, and we found those peaks. However, the problem, if we can call it as a problem, there is a so-called baseline or background. If the photons leave only part of their energy in the detector, like in this case, or in this case, there are no spikes, but a continuum. We call it as a baseline. It's not the same as detector background. It's a little bit different concept. Background means that we can measure gamma spectrum without any sample. So, how the activity is calculated. So, analyzers of the spectra have to take into account several things when they determine activity or activity concentration. These are the things that he or she must take into account. For example, correctness of the source data, sample type and quality. What do you want from what kind of result do you want from the spectrum? I mean, what are the nuclides to be analyzed? We are not usually analyzing all the nuclides, just the important ones. Spectrum quality, I mean that the quality that, okay, some peaks may be quite wide, resolution might be bad or something like that. In that case, the spectrum might be no good and we have to do another measurement. So we also have to take into account activity equilibrium of the radionuclides. I mean this, that in most cases we analyze, for example, if we want to analyze, for example, this iodine here, we detect the peak of iodine. But in some cases, if we want to analyze, for example, radon, which is possible for gamma ray spectrometry, then we do not detect peaks of radon. We detect peaks of its daughter nuclides. Okay? You are analyzing here natural radionuclides, but in some cases, at least in Finland, we might have some additional man-made radionuclides in the sample, and we also have to take into account detector background. I mean, this background is so measurement without any sample in the lead sheet. All right. So how to calculate activities? I will show you an example here, but let's see this. So this is activity, or this case activity concentration C, because of the sample quantity here. Quantity in terms of mass, in terms of volume, for example, per cubic meters or per kilograms or per liters. It depends on the sample. It may be water sample, then we calculate becquerels per liter. If it is air filter sample, then becquerels per cubic meter. All right. So the equation is very simple, basically. Very, very simple. So this is the peak area. How many counts are in the peak? Basically very simple. Then we divide it for the measurement time. Very simple. 1 day, 1 weekend. Normally in Stuk, at the weekends we detect, we don't change the samples, so the duration of one measurement could be 3 days or something like that. Okay. This is the library data. So it's a gamma emission yield of nuclide. This is perhaps the most difficult thing. We have to take into account detector efficiency. And I will explain this later, but it means that not all gammas go to the detector. Most of them goes in another direction, and we have to take that into account. And a lot of different effects. And then there are some corrections that must be taken into account. One thing is this coincidence correction that I explained. Also, decay correction must be taken into account. So when we report activity, we have to report also so-called reference time. Because nuclides are decaying, we have to determine the time to which this activity is calculated. So basically, this is very simple equation. Let's have an example. All right. Let's analyze the activity of cesium-137 in this case. It's this peak here, and the equation is here. So let's assume that the number of counts in this peak is 3,000. Please remember that you will get all these notes. Karuna Karavel will send these you later. Okay? Number of counts, 3,000 here. Just an example. Let's assume that the measurement time is 1,000 seconds, almost 20 minutes or something like that. On the basis of the library data, this is the gamma ray yield. How many gammas are emitted by one single decay. Let's assume that the peak efficiency at this energy, it is 0.02. So only 2% of gammas are detected. I will explain this later. And the sample quantity, this one Q, let's assume it's 1.1 kilogram, 100 grams. And let's assume that there are no corrections. I hope I understood or calculated this correctly. But the result is this, if you substitute these things to this equation. Not very complex issue, basically. All right. Let's look at very shortly about the peak efficiency things. So, this is photon energy here. It's a logarithmic axis. Logarithmic axis is also here. This is the so-called peak efficiency. So, we call our detectors as a short symbols. For example, here V6. It's name of our detector, one of our detector. So I made the calibration so that I have a sample beaker diameter like this, thickness around this, filled by water or almost water. We call this T20 calibration. It's our internal symbol only, nothing else. It is explained here. So what we do when we have a sample with different characteristics, for example, different elemental composition, different size of the beaker, we use so-called efficiency transfer software. I will later explain this part too. But how to interpret this efficiency function? Your function here is almost the same as this one. But you are not detecting very low energy gammas. You are detecting gammas above this point here in this area. This detector can go down to around 10 kilo electron volts. So let's assume that gamma ray energy is 100 kilo electron volts. So what's the efficiency? It is around 0.18 or 16 or something like that. It means that if 100 emissions happen, we detect, in this case, 16 or 18 gammas. So the efficiencies are not very big. All right, do you have any questions on that?
Question, because this is the efficiency is a very important parameter.
So it is important in the case if we want to have quantitative results, and that is our goal, of course. But we can, of course, we can sometimes just want to identify the nuclides. Then there is no need to know the efficiencies. All right, let's go further. All right, why the shape is like this? So let's look at first area here. So what happens in your sample? Nuclides decay, most of the gammas go out. Detector is assumed to be located here. So this can be called as a geometric detection efficiency. So most of the gammas doesn't reach the detector. All right, let's look at the gammas that reach the detector. Of course, in this case, it might happen that some photons go through the detector. And that is one of the reasons why this level is not higher. If the detector would be thick, then probably this part of would be much higher. So the maximum efficiency is 1. All right, let's look at closer small energies. So what might happen? It might happen so that all the gamma interactions happens in the sample itself. It is called as self-absorption. So we don't detect not very many photons. That's why the curve is decreasing very rapidly down there. And of course, some of the photons are absorbed in the detector window too, which is very thin, but it may happen. All right, what about this size here? It is because some of the gamma quanta pass through the detector, like this one, without interaction. And this way too. Or do not leave the full energy in the detector, like this one. There is Compton scattering, for example, and the gamma goes out. So this is the reason, these are the reasons why the shape is like that. Please note the logarithmic axis. Okay, there are several types of detectors. Some of them are not so efficient, for example, in low energy gammas. So this is the same curve as I showed you in the previous slide. This is the energy of lead 210. Emission energy is 46. This is the another detector with aluminum window. Window is quite thick, which means that these photons cannot go through the window, or only a small part. We call this detector as G2. It's an internal symbol. So can you explain, okay, you don't know the detector type, but can you explain why efficiency is here higher than for this detector, which is planar detector? Do you have any suggestions?
It will interact with the signals.
Yeah, the reason is that I don't remember the dimensions of this detector. Probably it's like that. So this B6, it's like this one. B6. I think that G2, it is something like that. So this is longer. I hope I'm correct, because I don't remember the details of all of our detectors, because we have 18 detectors of our lab, and I have a bad memory. Any comments?
Question?
All right, if not, let's continue. So I explained to you that very shortly this efficiency transfer method. I will show these things later, but these are the beakers that we are using in our measurements. Do you have these beakers? These are so-called Marinelli beakers. Okay, you don't have these. I will explain soon. But this is an example of one of our detectors, and can you see this one? The source is located here. Why? So I can say you that it was several years ago. I measured 1 gigabecquerel plutonium-238 source using this. So normally you cannot put on the detector megabecquerel sources. The so-called dead time is too large. But gigabecquerel is even 1,000 times more active. So this is plutonium source, but the point is that this plutonium nuclide, you can check this in the LARA application, it doesn't emit many gammas. So we wanted to qualify this source, what kind of source it was. It was used in some studies on biological things, how alpha particles reacts cells of your body. But let's neglect that. Okay. Regarding this beaker type, so it's a so-called Marinelli beaker. Why we are using those kind of beakers? Any ideas? So we want to have as high efficiency as possible, but we also want that number of or the mass of the sample is as much as possible. So we try to put all material as close as possible to the detector. So gammas may go from here to here or here to here. So this distance in those Marinelli beakers we are using is always the same, 3 centimeters. So the volume of this beaker is half a liter. We normally measure water samples using these beakers. Sometimes soil samples or other things. All right. So, what about the samples? What are the requirements? So, one thing is that the sample must be homogeneous if you want to have quantitative result, correct quantitative result. So we have to know the density, height of the sample, and also the elemental composition, so that this our efficiency transfer method works correctly. You have a little bit different approach in your laboratory here. So we have only one efficiency calibration of each detector, except those Marinelli detectors. We have some of these too. But I think you have several calibrations. You mentioned, is it 16 or 18 calibrations?
Yeah, more than 10. We have RGU, RGK, RGTH.
What is asking the type of container? Yeah, we have containers in 5 gram of sample, 25 gram, 125 ml, 250 ml like that.
Yeah.
And we have sample holder for air filters.
But,
Disc type.
but in those cases you are using, if the sample size varies, you use different calibrations in the background.
We have reference material in the same geometry.
Yeah, yeah.
We can show that.
But my point is that, I will show it here. So, in the beginning, when I came to Stux Gamma Ray Lab, we had a more or less same kind of system as you have. Okay, we have 18 detectors. Each of the detector, if it would be the same case as you have 16 calibrations. If we want to take into account the coincidence effect, which means that we should also, I will explain this later, we have to also take it into account so-called total efficiency, which means that the number of calibrations is, I don't want to multiply this just now, but the number of calibrations would be too large. My job would be so that I would do nothing else but calibrations. It's a waste of time. Then I decided what to do, and that's why we are using now this efficiency transfer program. I will explain that later. All right. So we also should know the elemental composition too, because it affects the efficiency in case of low energy gammas. I will show that part also later. So this is a homogeneous sample, this one. So the nuclides shown here as red spots are homogeneously distributed. This is not a homogeneous sample, because there are a set of nuclides here, not here. This is either from the point of view of gamma ray spectrometry, it's not a homogeneous sample. Basically it's homogeneous, but surface is a little bit tilted. This is a little bit how to say, not a normal case, but if we want to determine radium concentration or radon concentration. So what happens in case of radon? It may go to this place, and if we want to analyze radon daughters, so most of the radon goes here, not much here. So this is not very homogeneous from the point of view of gamma ray spectrometry. So the sample must be homogeneous, like this one. So, as explained later, I want to explain this later. What does a gamma spectrum analyzer do? So, at first, the analyzer checks the validity of the sample data. I mean, beaker type, is it correct? I mean, this refers to the efficiency. Is the reference time, is it okay? We have seen some mistakes happened. Is the so-called quantity, it's not a quantum, but it's a quantity of the sample. Is it okay? Is sample density okay? And some other relevant information. So in this phase, the the analyzer do not necessarily check the spectrum itself. He or she checks that the basic data for the sample is okay. In this case, I'm sorry that this is in Finnish, but this is the sample description we are using it for this sample. It's a Marinelli beaker. This is so-called reference day for which we calculate the activity. This is the amount of water, in this case. It's 1.7 liters, yeah. Then there are some other information. Measurement was started at this time. Its duration was almost 1 day. This is detector so-called G4 and using Marinelli beaker. Height of the sample, 3 centimeters. Density, because this is water sample, density is 1. But in this stage, no spectrum analysis, not yet. We have to check the validity of the basic data at first. But then we have to go to the analysis of the spectrum. All right. In my organization, we do the spectrum analysis automatically. So it means that there is a process that identifies each peak and calculates the activities. So it's an automatic process, but we have to check this process or the result of the process manually. For example, like in this case, it might happen that the peak shape is incorrect because of some reason. For example, in this case, the peak area is 3,500. We can do manual analysis, and the correct value is almost 6,000 counts in this peak. All right, some samples may contain very many different radionuclides. This is an example of quite challenging gamma spectrum. In this case, there are almost 200 peaks. I have seen some spectra that contains 400 peaks. So it's a very tedious work if we want to analyze all these. But normally, we analyze only some of these nuclides. But let's look closer at the peak, at the energy of this. All right, you can see the peak here. I think that at least some of you knows what is this peak. So there is uranium-235. Emission energy is shown here, quite close to 186. But there is also radium-226. Emission energy is practically the same, but the yield is very small. In this case, peak fitting, okay, it may look like quite nice, but we do not rely on this because the peaks are overlapping too much. This is typical in sodium iodine detectors. Resolution is quite poor, but these things may happen in high purity germanium detectors too. Not very often. So in this case, if we want to analyze radium, we will analyze radon progeny. Lead 214, bismuth 240. But how to analyze, or what are the requirements of the sample? Because our normal beakers, they are wrapped in this case as a foil, because they are not gas tight. And you can see radon disintegrates to radium, disintegrates into radon, which subsequently decays to lead and bismuth. The problem is this radon. It may escape from the beaker. I think that, is it so that your beakers are quite tight?
Seal it with
You seal it? Yeah.
and cap it tight.
Yeah, all right.
Although it is tight, we seal it.
We use vacuum packaging. It's a very simple process. But what we do is that at least the beaker must be full of sample to avoid inhomogeneity, and to ensure that there is equilibrium between radium and its daughters. We have to wait 3 weeks. Why 3 weeks? So the reason is this one. Half-life close to 4 days. We want to have equilibrium. This is the reason here. And this is very important. You have to, if you are using this decay chain or mother-daughter analysis, you have to verify that there is equilibrium. Because, for example, for these nuclides, uranium-238, thorium-234, and protactinium-234M, they might be in equilibrium or not. But this is quite difficult thing in some cases, because for example, some biological vegetables may absorb, I don't know the correct term, but I call this as absorption. They are absorbing thorium very much, which means that there is excess of thorium in relation of uranium. Well, you can, in this stage, if in this phase, if you want to have equilibrium, what could be the waiting time? Any idea? 24 days. How many months?
6 months.
Okay, 6 months. Quite okay. Then there is equilibrium. But in this case, you do not need to wrap the sample, because these are not gases, they are metals, they are not escaping from the sample. All right. So, advantage of gamma ray spectrometry is that in principle it can be used to detect almost all radionuclides, but there are some exceptions. The gamma yield must be large enough. For example, in case of plutonium-238, the yields are very small, so it's quite difficult to detect plutonium-238. However, alpha spectrometry is much better. You can see these are the energies of alphas, these are the yields. Total sum is 1 in this case. Total sum here is not 1 in case of gammas. So that's why alpha spectrometry is better than gamma ray spectrometry. But you have to do sample processing, which is very tedious process. All right. So, one slide summary. Why gamma spectrometry? It's a good determination method because with the exception of a few radionuclides like tritium, carbon-14, strontium, almost all radionuclides can be detected by gamma spectrometry and by using just a single measurement. However, the measurement time in some cases must be long enough. All right? The method detects radionuclides with short lives very sensitively. This means that the nuclides sends automatically information from themselves. We don't have to kick them. Please send us information. They send us information by emitting gammas, alphas, etc. However, in case of some nuclides like thorium-232, uranium-238, they send us information too sparse, too slowly. That's why ICP-MS or alpha spectrometry might be better. Advantage is also that sample processing is very simple. Just put the sample in the beaker. Well, this is not exactly the thing. For example, in Stuk we dry all the samples very carefully. Sometimes you have to ash, you have to burn the sample and put the ash into the beaker. But it depends on the case. But basically it's a simple processing compared to the radiochemical processing used in alpha spectrometry. So I already explained this. So it's a so-called passive method, which is not a good definition because we actively do something, but the point is same for alpha spectrometry. All right. This is my last slides. Do you have any comments? Is it too simple? I tried to explain same thing that Avanes told you yesterday. Please note that you will get these presentations later, so maybe you would like to see them again. Please.
Okay. So you showed me about the equilibrium between the uranium and the proactinium or something like that. Yeah. This thorium and proactinium. So is that ensured in soil samples?
In soil samples, I have thought this a lot, and it depends on the case. For example, if it rains a lot, and the rain might contain acid, a little bit, not much. So it may happen, I'm not a chemist, I don't understand these things very well, but thorium might, what's the concept in chemistry? Leach, yeah. So leaching may be different. in those cases. But in case of rock samples, then I think it's leaching is not. But you have to have every time this think about this equilibrium. Leaching is a very relevant thing.
Now, if those are if I assume that is in equilibrium, then I can give my radium results as uranium. Am I right?
If there is equilibrium, then you can use this nuclide or this nuclide for results of this and this. But if there is no equilibrium, then not.
No, what I'm asking is, I only measure radium-226.
Yeah.
So suppose I assume the equilibrium between all the radium.
Yes, if there is full equilibrium in the sample, full equilibrium, then each radionuclide has same activity. This is in the case of rocks, for example, but not necessarily in soil, plants, because there are biological effects, geological effects, very many different things. So equilibrium is very important. All right. Any comments? Yeah, I will go closer. Yeah.
Suppose I have to measure radium-226 in a soil sample, then the efficiency calibration will be done using a radium-220 source.
Not necessarily. Let's go back. So he asked about the efficiency calibration of radium-226. Where is that? Let's go here. So, how, if I understood correctly, his question is that how to do efficiency calibration for radium-226 for 186 peak, because there are two nuclides, uranium-235 and radium-226. So the idea is that these points here, they are measured points, but there is no radium nuclide in the original sample. We got this sample from NPL. It's a primary standard laboratory in Great Britain. So it's a primary laboratory. They know the activities of nuclides very well, and there is no radium in that sample. However, we can fit a curve here. 186 is close here. So, in determining the activity, we use that curve, not those points. If we calculate the activity by using this. So efficiency is strongly dependent on the energy. Is this the question that you wanted to know?
But if I consider the 609 peak of bismuth 214,
Sorry?
sir, if I consider the 609 kV peak of bismuth 214, then what should I do for the efficiency calibration part?
So, if you want to, it's a bismuth 214. Yeah, bismuth has several peaks, which are located 2, 3, 4, 5, 6. They are located somewhere here. So then you use that efficiency of these energies. So you have to know the energy. Practically, activities are calculated by this. Too many slides. Practically, activities are calculated on the by using the software. Jenny, in your case. So you do not need to know the efficiency. The program should take the efficiency automatically into account. However, we should have correct curve for the sample in question. So this curve is valid only for this geometry. Beaker size like this, thickness like this, and there is practically water in that beaker. But I think that you will be, that Avanes will much more explain this point in laboratory session. Yeah.
So we do the same thing, extrapolation and then taking them.
Yeah. Yeah.
I think today you're going to do that. Yeah. Got it. Is there any other questions?
All right, I think that this is it. Please ask me later if you want.